Welcome to this 8th lecture video for Physics 4A. This is the second of two sets of lecture videos in which we will showcase examples of solving force analysis problems with the four-step process that we call standard strategy. As I said in the previous video, there are more examples of questions that can be solved by the application of standard strategy than we can list in these two sets of lecture videos. So I encourage you to try other problems on your own and look for additional examples that have been provided elsewhere in the course. In this video, we will look at an example of interacting bodies that demonstrates the power of a standard strategy as a problem-solving tool. In the example, you will see a block on an inclined plane with a twist that the inclined plane can move. Then we will shift focus and finally cover uniform circular motion. We will first start with a brief explanation of the centripetal acceleration with reference to Chapter 4 material on circular motion kinematics. Then we have a series of examples which highlight some important concepts and ideas involving circular motion. The spinning bucket problem serves as a physical example illustrating the acceleration, that is, centripetal acceleration, that you should come to expect in problems involving circular motion. Then we look at a merry-go-round setup to discuss what additional complications arise when or if you use rotating reference frames and centrifugal force. Finally, we will wrap up with two examples of application of standard strategy in situations involving circular motion. This is a long video set. Do please take your time watching through and understanding the examples covered in this set. Okay, so this is the question that you see linked from the lecture page, and it shows the value of the multi-block problem-solving strategy because the kind of question that's being asked here. If you're trying to answer it using only your intuition, you will find it difficult. There are aspects of the question where intuition alone gets you only so far, and undisciplined, disorganized problem-solving strategies, which, for a lot of you, you are smart, you know how to figure things out yourself, and that might have gotten you quite far. But at some point, it's like in sports, having a proper form in doing a particular task. So this is the setup. You have two blocks that can potentially move relative to each other. I think it says, all surfaces are frictionless. So I have a ramp of mass m that's sitting on a tabletop. And unlike a usual circumstance, this is free to slide. And I have a block of mass m that's sitting on top of it. And I think this is a good thing to simulate in algorithm. So let me do that. So let me draw those objects. Let's see here. I need some way to draw straight lines. Okay, so we have a ramp. And let me just have a small block of some mass. Let's see here. Okay. Let me make all surfaces frictionless. Then I think most people have some intuition for what these blocks will do. If I simply let go, simply let the simulation run, and blocks do this. The ramp moves to the left, the block slides to the right. Yeah, and the setup of this question is okay. We are going to do different things. Apply some force to the ramp. And as we apply some force to the ramp, what kind of stuff happens. So so we've just done what happens if we apply zero force. Okay. Um, let's see what happens if we start applying some amount of non-zero force. So, oh, I don't know the amount here. Let's start out with the 5 newtons. See what it does if I apply 5 newton of force. Okay, the block still slides down. Now, I guess the 5 newton was enough that the ramp doesn't get pushed to the left. It ramp slides to the right. And let's just increase the force and see if anything more interesting happens. Increase the force to 10 newtons and see what happens. I think all this green is really clashing with my color sense. Let me just change the color for this thing. Right, I think that's better. Okay, so I'm applying 10 newtons on the ramp. All right, nothing has changed much. Let me go up to 20 newtons. I don't know. I haven't done this ahead of time, so I don't know at what forces we would have some more interesting thing happening. Okay, with the 20 newtons, something has changed. So, I mean, this is sliding down still, but it's not sliding down as quickly. Okay, let me try increasing this force up to 30 newtons. Oh, so at some amount of force, you see this block actually sliding up. And I hope this agrees with your intuition that you have enough of a real world experience with some way, and you can draw from similar experiences where you have some kind of a wedge, you have something that's sitting on it. If you really push hard on the wedge, then things slides up. Those are two different things happening depending on how hard you push on the wedge. With the 30 newton, it slides up, and with a smaller amount of force, it slides down. That those things happen. It's the fact that those things happen that agrees with your intuition. So we did that demonstration and assertion that that's how it should happen. Now, what we want to work out is, okay, so you have some phenomenon that depends on how much force you apply. And the question is there an exactly right amount of force you can apply with which the block will stay at rest relative to the ramp? More precisely, meaning it won't slide up or slide down. So so that's the question, and so we basically went through A and B, and so now we will find how much force F to apply so that the small block M does not slide down the wedge. So so let's work through the standard strategy to figure this out. And if someone simply asked, what force F do you apply so that the block doesn't slide down, this is where I hope you will see the limitations of just intuitive approach. Because with the intuitive approach, I think people can maybe get as far as this. You can get as far as saying Newton's second law, force is mass times acceleration. So big mass. So you maybe have enough intuition to say you should be considering the total mass, and then you have it times by acceleration. And intuition will get you maybe this far and no farther. And and in this expression, you have two unknowns. You have the applied force that you don't know, and you have acceleration that you also don't know. So, um, so this is the limitation of um, non-systematic problem-solving approach. So we'll approach this systematically. The standard strategy that we teach. The first step in standard strategy is drawing the free body diagrams. Here we have two objects, so I'm going to need to draw two free body diagrams. Let me do that. I have a free body diagram of the ramp, and I have the free body diagram of the small block. I will go through drawing the forces quickly since you've done this many times. I don't need to really belabor the point of You start out with gravitational force, and then you keep asking yourself, did I draw all the forces? And well, I need to apply the force F, and I do know the ramp is not accelerating, in this diagonal direction. So for the ramp to accelerate horizontally, there must be normal force. And you might think you drew all the forces here. Let me move on to the next free body diagram of the small mass M. And, there's still gravity acting on it vertically. Now the surface of contact here is angled, so I have to have that angle in mind and draw normal force this way. Oh, wait, it's two different normal forces. Let me draw this N1, N2. And if the ramp is accelerating to the right horizontally, then if the small mass m is neither sliding down nor up, then it must be accelerating the exact same way, so, horizontally, with the same magnitude of acceleration as the ramp. And with these two forces, you can make the forces add up so that the small mass m has horizontal acceleration. That looks fine. And now the most common mistake people will make here, and this is the kind of thing that's difficult to get intuitively, is people will forget about Newton's third law. So you have to do Newton's third law check, by which I mean, for every force that you have in your diagram, you need to either be able to characterize it as an external force, meaning force being applied by an object outside of your system, or if it's an internal force, you need to be able to find the action-reaction force pairs. So for a lot of the forces, they will be external. Gravity is an external force because it's coming from Earth. I'm not drawing free body diagram of Earth. Applied force F is also external. Whatever agent is applying the force, I don't have diagram of that agent. Normal force 1, that's coming from this surface of contact here, so it's also external since I'm not drawing free body diagram of the tabletop. And this normal force here, it's coming from the ramp, which means it's an internal force. So I must have a reaction force on ramp by the block M. And I'm going to use the same label here because this is really the usefulness of Newton's third law. Once you identify a pair of forces as action-reaction force, then you can immediately say that their magnitudes are the same. A lot of students kind of get them backward. You start by looking for equal and opposite forces and try to pair them up. No, it doesn't work that way. You first find the pair of forces that describe the interaction between two objects. And once you find a pair, then you can say they are equal in magnitude. So, okay, so that's my complete free body diagram. Okay, that's my step number 1. Always the step that takes, if it doesn't take the most amount of time, it should take the most care. Again, forgetting this Newton's third law pair, it's a common mistake that I've seen people make, and it comes down to lack of care. Okay, so step number 2, I need to define my coordinate axis. And this is actually a tricky part with this question because it comes down to your direction of acceleration is unusual. Whenever you have an incline, people are used to seeing acceleration go down the incline. And sometimes people kind of automatically go into that groove, rut, and, pay attention to your direction of acceleration. Horizontal acceleration means that you want to choose horizontal as your x direction. So surprisingly to, I think, many people who might not have seen this question before, here you want to choose a straight axis so that your x-axis is along the direction of acceleration. And I guess for the ramp, it's not all that surprising that you'd also choose a straight axis. Okay, so with those axes chosen, you now need to do step number 3, decompose your forces into components, x and y components. And you see that, okay, so I need to decompose this N2 into x and y components, and I think that's the only force. I guess that's nice. So this is the x component, this is the y component, and I try to draw this in a way that I can now see the triangle with this angle here. That might not be the angle I know. Okay, I need to be careful here. Let me just carefully draw auxiliary figures that highlight what angles I know and how that angle is corresponds to the angles in the triangle. So the angle that I'm given is the angle of incline, which might be given as this angle here. That's my theta. So let me just track through a few angles here. So this angle here is 90 degree minus theta, which means this angle here is also theta. Oh, I guess I could have done it directly. Whatever. So, okay, this angle here is going to be 90 degrees minus theta because it's 90-degree angle, which means it's this angle here that's actually theta. Okay. And this exercise is something that you should go through for every setup, every situation, because exercise meaning drawing the right triangle that shows the decomposing of the forces, and then you go through this geometry exercise of which of these angles are theta. Because uh, people sometimes get into habit of just associating x with the cosine and y with the sine, and doesn't all it maybe works out that way 50% of the time. So so I decomposed my forces and I identified this angle theta. And I guess I might as well do this step of writing down the expression for the magnitudes of these components now. So the magnitude of the x component, since it's on the opposite side of the angle, it's n2 sine theta, opposite side of the angle. And for the vertical component or the y component, since it's the adjacent side of the angle, it's n2 cosine theta. So yeah, here in this particular case, the x component turned out to be cosine theta, not cosine. And these components will be exactly same for the N2 in the other free body diagram. I guess that's maybe one benefit of having the same coordinate axis, because whatever decomposition you did in one should also match for the other. That may not be the case if some of your axes were not pointing the same way. Okay, that's step number 3. Now we are finally ready to step number 4 after, I don't know, 10, 15 minutes of considering this question. In step number 4 is where we write down Newton's second law equation. This is our primary problem solving tool. We write down a system of equations, and in that system of equation, we are hoping that we have the same number of unknowns as equations. So let me write that. So I have 2 objects moving in 2-dimensional things. So I have potentially up to 4 equations to write. I need to write down net force for the ramp in the x direction, net force again for the ramp in the y direction, and net force for the block in the x direction, and net force for the block in the x y direction. And some of these equations might turn out to be trivial. In this case, I don't think that'll be the case. So let me just write the 4 equations and see what I have. I have so net force on the block ramp in the x direction. I have the applied force F minus going in the negative x direction, the x component of n2. I wrote that as n2 sine theta. So minus n2 sine theta, that out to equal the mass times acceleration. Okay, let's keep going. Net force in the y direction. There's a few. I have the normal force n1, and then I have the downward forces, the y component of n2 and mg. So minus n2 cosine theta minus big mg is equal to 0. We are not accelerating vertically. That was the whole point of why we chose our axis the way we chose it. Okay, let me write this down for the small block. So horizontally, oh, there's only one force, N2 sine theta. That's the entirety of um, horizontal force for the block. That should be equal to small m times acceleration. And then we have y components of forces again, N2 cosine theta minus mg is equal to 0. So this is the what I call end of a standard strategy. Again, standard strategy, it doesn't so answer the question for you, but it hopefully leaves you at a place where you have enough information to answer the question in a few more steps, just going through the algebra. Let me check to make sure I have enough information. So I have one, two, three, four equations. So my hope is that I have exactly four unknowns, not less, not more. Let's see. Apply the force F, I don't know, so that's one unknown. N2, I don't know, so that's two unknowns. Theta, I'm given. Mass, I assume I know it, or I can at least measure it. Acceleration, I don't know that. That was the objection I raised here, that this equation is in terms of two unknowns. Okay, three unknowns so far. N1, I don't know that either. Don't automatically say N1 equals mg because it actually that isn't even right. And even if it's right, you would have an equation that illustrates that. So you still count it as unknown. I think I counted all the unknowns. All the other symbols are already counted. So I do have four unknowns, which means yeah, I have um, I have four equations, four unknowns, so it ought to be solvable. And the biggest challenge at this point is going through the algebra. A system of four equations is quite a large system, and it's one of those things where unless you plan and go through these steps deliberately, you can easily get stuck in a loop. So let me illustrate that algebra since this is one of the rarer circumstances where the algebra itself could be tricky. So this is how I like to plan my algebra. So we are looking for a particular quantity of force that is required to do something. That was our whole setup of the question. So what that means is this force, I'm looking for it, but it's the thing I want to solve at the very end. Because at each of the intermediate solution steps, what you're going to see me do is I'm going to solve for an unknown, and I'm going to use the solved expression to eliminate the unknown from all my other equations. So that's why I want to solve for force at the very end, not at the beginning or intermediate. It's kind of counterintuitive because the quantity you want is what you hold off solving until the very end. So I see here, so this is one of the equations that has acceleration. So I think I am going to solve for acceleration here and plan to plug it in there. Yeah? And so then I'm going to have N2 as an unknown. And even though I do see N2 here, this equation is not going to be useful because it has another unknown N1. So when I solve this for N2 and plug it in, I will just have exchanged the N2 for N1. And that doesn't really advance my goal. And looking farther down, I see this equation, which has no other unknown other than N2. So I can solve for N2 here, plug it in into all my other expressions to eliminate N2. So let me do that. So I'm going to do solving equation 3 for A and plug it in here first, and then do the thing I just described. You can do this in different order. I think the important thing to realize here was that equation 2 is kind of useless, so I'm not going to work with this at all. I mean, if you wanted to find the N1, equation 2 is useful, but I don't care about N1, so I'm just not going to involve equation 2 at all. So, okay. So from my equations, let me slow down and go step by step. So from my equation 3, I have this expression. I'm solving this for acceleration. My acceleration is n2 sine theta over small m. I'm going to plug that into equation 1. So with the equations 1 and 3, I get this expression that has only two unknowns, f and n2. F minus n2 sine theta is equal to big M times this expression for acceleration and 2 sine theta over m small m. Well, let me simplify it a little bit because I see an easy simplification. If I move this over to the right hand side, then I have this plus n2 sine theta. And I think I can actually factor out n2 sine theta. And when I do, this is the whole simplified expression. Force F is equal to n2 sine theta times big M over small m plus 1 here. You can distribute it back and double check that I didn't make any mistakes. Now we have this n2 that we can eliminate n2 using equation 4. So from equation 4, I have n2 is equal to m small mg over cosine theta. So plugging that into here, what I get is small m times g sine theta over cosine theta. So let me write that as tangent theta. And times big M over n plus 1. And if you really want to simplify, you can simplify it a little bit. I see that if I distribute the small m in, then I get cancel this out, and this becomes small m. So sum of the masses times the g tangent theta. And that's the kind of result that you wouldn't guess intuitively. And if you compare this with this intuitive thing here, you do see some of the matching things. I have this some of the masses. So I guess the acceleration must be g tangent theta. And if I go back to these equations and solve for acceleration, you should find that acceleration is g tangent theta. So intuition is completely worthless, but it doesn't take you quite far in solving complicated setup like this one. For a complicated setup like this, really the solution approach you need is the systematic problem solving approach that we teach, what we call standard strategy, or your textbook and the portable tape uses different names, but they all refer to the same multi-step systematic approach. The systematic part is geared at coming up with this system of equations. And once you have the system of equations, then the rest is algebra. And even when doing the algebra, it does help to be systematic. But I think algebra portion is easier because if you get stuck, then you keep trying different approaches, and eventually you will get at the correct result. But in coming up with these equations, unless you have the right approach for doing that, like without the equations to solve for, you are stuck. In this video, we will briefly go over centripetal acceleration. In section 4.4, your textbook covers uniform circular motion. And the key result in the section is the derivation of centripetal acceleration in terms of the speed of the uniform circular motion and the radius of curvature, r, of the circle being traversed in. And you could leave it there. That's a formula for you to memorize, and you use it whenever you see circular motion being mentioned somewhere. But I want you to take a little bit of time now, because the circular motion happens to be a place where you see acceleration unexpectedly. So this will become more important when we get to forces, because many people intuitively do not expect a net force because they don't think they are seeing acceleration in a particular situation. And what I wanted to emphasize was that whenever you see circular motion, there is always acceleration. And that is best illustrated by figure 4.18. So let me use this figure to briefly sketch the argument for centripetal acceleration derivation, which is also done in your textbook, but I think this is a good opportunity to highlight the usefulness of the vector description of motion. Okay, this is figure 4.18, and it's showing movement of an object from one position to another position at a later time over a duration of time. As the particle follows a circular path, the instantaneous velocity vector will always be tangent to the path. So that's why the velocity vector is drawn tangent, that is parallel, that's not the right word, tangent to the circle at the point represented by position of the particle. Then, since as the particle goes in the circle, the direction that is tangent to the circle changes, you see that the direction of the velocity vector necessarily changes. This is called uniform circular motion because the speed is assumed to be constant. So the length of the velocity vector doesn't change, only the direction does. I've drawn a copy of the velocity vector here. And through geometry, you can figure out a few things. So the tangent direction to the circle is perpendicular to the radius. And what that tells me is, since you have 90-degree angle here, this is the 90 degrees minus delta theta over 2, because this is delta theta over 2. So the angle here is delta theta over 2. And these two arrows that I've drawn are parallel to each other. That's what you get when you translate a vector so that you draw the same vector elsewhere. That means this angle here is also delta theta over 2. And the angle here is 90 degrees minus delta theta over 2 for the same reason as below. And looking at this straight line here, the angle here, when added to the other two angles, should be 180 degrees, which means the only angle this can work out is delta theta over 2. And that's how they get this figure here, with delta theta between the two velocity vectors. Now, here's a fun thing. These two triangles are both isosceles triangles with the same angle between them, delta theta. So they are similar triangles. So you can use methods of geometry to figure out what delta V should be by relating it to delta R. And once you have an expression for delta V, then you can get the centripetal acceleration by saying that that's delta V divided by delta t. And of course, for instantaneous centripetal acceleration, we take the limit of delta t going to 0. And big part of this ends up being somewhere along the line saying that delta r, the magnitude of the displacement, is equal to r, radius of circle, times delta theta, which is true only when delta theta is very small, because otherwise this expression is actually giving you the arc length. So only for small angles you can say that arc length is about the same as delta r. You can read the detailed derivation in the textbook, but I want you to highlight this to show how geometric reasoning, which is the vector description of motion, is helping you analyze this situation. Finally, I want you to point out one resource to help you start developing intuition for centripetal acceleration. This is a website you have seen before, PHYS, and the simulation is called Motion in 2D. It's a Java simulation, so you need to have Java installed in order to be able to run this simulation. the simulation does more than just a circular motion. It has a few presets that will allow you to show what linear acceleration motion or motion with linear acceleration. And circular motion looks like. And it'll take some time to develop your intuition for centripetal acceleration, because this is the acceleration that you see when nothing seems to be speeding up or slowing down. So it's easy to miss it unless you are constantly remembering that whenever you see circular motion, like right now, you have acceleration.
It's actually problem 5, not 4, because 5 is more fun. I have an actual demo for that. Problem 4 is, we'll talk about it because it's important. Actually, problem 4 relates to, so I told you earlier in the semester that we are never going to deal with the pseudo forces in this class. And problem 4 is one of the earliest example why we shouldn't deal with the pseudo force. So we'll do problem 4, but I have an actual bucket that I can put water in and actually spin. So let's do problem 5 as a fun demo. So you guys kind of know what would happen if I took this. Let me clean up my sink. If I took this bucket and turned it upside down, right? What would happen? Yeah, water would fall down. Everyone here believes in gravity. So now, from your experience, do you have any sense what would happen if I took this? Let me do it over there. I don't want to damage the projector accidentally. So do you have some sense what would happen if I took this and if I spin it? So if I spin it all the way around one full circle, will the water drop out?
No, if you go fast enough.
Yeah, let's see. Yeah, if I go fast enough. And in fact, the question I'm interested in, how slow can I go before the water will start to fall out? So let me try going, slower and slower until water will fall out. So now, that wasn't very fast, but water barely starts to fall out as it's going over, right? So what's happening to the water? When I'm going fast enough, why doesn't the water fall out? Is there no gravity at the top? So I would like to analyze this picture. So let me draw a figure and let me draw the figure and let's try analyzing it using the physics that we know. Because the promise with the circular motion and centripetal acceleration is that we are not actually introducing any new physics. I said this last time, even the centripetal acceleration and centripetal force, there's nothing new that I'm bringing in. It's just a mathematical analysis of something that I already had. So somehow we should be able to make sense of this bucket without introducing anything new, without introducing anything that we didn't already know. So let me call this worksheet 5, problem 5, spinning bucket. So I'm going to draw the picture of the bucket at a snapshot, just the moment when it's at the very top. So I will draw it as a snapshot. There's water here. But what I want you to remember is that even though I'm drawing it as a snapshot, you kind of should remember that this bucket is moving, that it has a velocity v that keeps it moving in a circle. Good. All right, so let me redraw the bucket. I don't actually need the 2 strings. All right, so I'll just pretend that I had only 1 string. All right, so we would like to figure out what forces are keeping this water in the bucket, because it's apparently not falling out, right? So what do you do when you are trying to analyze the forces? Something you have to do for exam 1. Where do you start? You start out with a free body diagram. So we are going to try to apply standard strategy because this is apparently a force problem. So, hopefully standard strategy will work. So, all right, let me start out with the free body diagram of water. Even though the water is it's a liquid, I'm going to treat it as if it's one solid object. Or if that bothers you too much, you can pretend that I did this. Instead of having water in the bucket, I mean, I do water because it's more dramatic, but I could have actually put a golf ball in the bucket, and it would have been the same thing. Do you see the golf ball at the top? Ooh. Sorry, that's why. So let me do it with this one. The tennis ball is easier to see. So I could have done the exact same thing with the tennis ball. When I spin it, do you see the tennis ball staying at the bottom of the bucket or at the very top as I'm spinning it? It's not falling out. So so for the purpose of the analysis, we'll treat water like it's a solid. It's one single material instead of liquid that might pour out. So let's say this is my representation of water. So question is, what are the forces on the water? Always gravity. Somebody was whispering gravity, right? Yes, okay. So there's going to be gravity pulling it down, right? All right, let's keep going. Any other forces on the water? Normal force. Okay, it has 3 walls, right? I'm going to say normal force from the left and the right walls. They will cancel, balance out. So I'm only going to worry about the normal force from the bottom of the bucket. What direction is the normal force? Yeah, normal force only pushes away from the surface. So normal force will, okay, all right. That's not exactly helpful in keeping the water up. Any other forces on the water? Anything else that's touching the water? That the normal force is from bucket. It's touching the bucket, not the water.
Centripetal force we have.
What's touching the water to give you the centrifugal force?
Here.
So you think if I did this in vacuum, water will fall out? Not really, right? Or if you imagine doing it with a tennis ball in vacuum. The question comes down to, is the air keeping the tennis ball up? No, right? So the air is touching it, but right now we are essentially neglecting air resistance. So once again, is there anything else that's touching the water to exert any other force that's not drawn here? Yeah, there's no other force. Meaning this is the complete free body diagram. There's no other force that we didn't identify. Now, using this diagram, we can talk about it a little bit. So this gravity, it'll always be mg, it won't go away. But this normal force, that could change, right? So let me probe your intuition this way. Imagine I have this bucket, and the water in there. And imagine I'm spinning this really fast versus when I'm spinning this relatively slow. How do you think normal force varies between when I'm spinning this fast and when I'm spinning this slower? Do you feel like normal force should increase or decrease as I spin it slower and slower? Decrease, that there's less of a push, right? So, which means as I spin this slower and slower, so this is what I was trying to do last time, that, try to get the water to fall out. So as I spin this slower and slower, one thing I can imagine happening is that this normal force would decrease to the point of 0. So at this point is when the water is about to fall out. Does all of this make intuitive sense? Yeah. In fact, when there's no normal force, that's when moment when there's no contact force between the bucket and the water. So the water is about to fall out really in that situation. All right, so this is the complete free body diagram of water that's about to fall out. I want to make sure that this makes an intuitive sense with you, that if I'm spinning bucket this way, so at this snapshot, the gravity is pointing downward, there's no other force, and the water's not falling out of the bucket, and all of this is okay. This is the correct picture, by the way. I think the only part that might be misaligned or incorrect is for many of you, this might not sound intuitively true. And that's the part I want to provide some guidance to. So let me put it this way. What would it mean for this free body diagram to be actually correct? Like, what kind of consequence do you see from saying that this free body diagram is the correct free body diagram? Like, what are we drawing free body diagram for in the first place? I mean, okay, the object, what's the reason that we are drawing the free body diagram? Tickle first.
To map all the forces that are applying on the water.
Okay, map all the forces, and then you can find the net force. Why do we care about net force again?
Direction of acceleration.
Acceleration. Not only the direction, but the whole acceleration. Because of Newton's second law, right? Net force is equal to mass times acceleration. And this acceleration is why we care about the net force. So here, you see the net force, the single gravitational force. So you see that acceleration. This is the acceleration that this free body diagram says is, well, that's what it is. So does it make sense to you intuitively that the water here, which is going in a circle, not falling out of the bucket, it's in fact at the same radius from this point, that this water is accelerating downward? Okay, so tell me how it's accelerating downward when it's not. So, I think I'm okay with something that's at zero velocity. So, this water is at zero vertical velocity. I'm okay with that having downward acceleration because that's like this and then dropping like this. Here the difficulty would be, well, it's not dropping like this. It's moving in a circle. So tell me what you can point to and say this is why I expect downward acceleration.
So we're going in a circle, accelerations towards the center.
Yeah, we are going in a circle. That means there has to be centripetal acceleration. So that's what I find is the most tricky part about circular motion. You see accelerations where you didn't expect to see any. So this is moving in a circle. It's moving in a path like this, right? So what that means is that every point of this path, it has a centripetal acceleration. Here, it has centripetal acceleration. Here, it has centripetal acceleration. Here, it has centripetal acceleration. And at each of these points, the magnitude of centripetal acceleration is given here. Centripetal acceleration is equal to v squared over r. So if anything is moving in a circle with some non-zero speed, then it's accelerating. So learning to expect that, I think that's the biggest hurdle in doing well with a circular motion. So here, I should have expected the centripetal acceleration from the beginning because it's going in circle. Now, once you are expecting acceleration, then this is all perfectly fine free body diagram. It's saying that, well, to have this acceleration, I need this force. So another way to put it is that this force that we have identified, we could call this centripetal force. This is the force that's keeping the water moving in a circle at the very top. Right? Okay, question, comment? Yeah.
You said even though it's moving at a constant speed, it's accelerating because it's changing the direction.
Changing the direction, yeah. I mean, that's not surprising, right? It's that when you start to apply it, there are ways that expectation for the acceleration can be hidden. That's why you have to learn to watch out for it. So let's finish this problem. It asks identifiable quantities. Oh, what is the minimum speed so that the water doesn't fall out? So we already drew the picture where the water was just about to fall out. If I go any slower, the water might fall out. So this is the picture where water is about to fall out. Force is mg. And so from that, we can say the net force in the vertical direction is, I'll say downward is positive, is equal to mg. And that's equal to mass times acceleration. Here, do we know what magnitude of acceleration, or do we have a way of re-expressing this acceleration? Yeah, as centripetal acceleration. So that will be a common feature you see in circular motion problems. You will have some expression that involves acceleration, and then you'll kind of be stuck there until you remember acceleration is also, centripetal acceleration is also given by this. So you can say v squared over r. Then now it relates to the radius r and the v that we are asking for. So we say this is equal to mv squared over r. They gave us r, right? Quantities needed. All right, one of the quantities we needed is the radius r. That's one of the quantities. So yeah, masses cancel out, so I don't need to know the mass of the water. I can solve for v. And when I solve for v, I get v is equal to square root of rg. Good? That's it. Pretty simple question. It's conceptually difficult because you have to get used to starting to expect whenever you have circular motion, you will have centripetal acceleration, even when the picture doesn't look like there should be any acceleration.
So this is a scenario that's kind of good to consider in an attempt at reconciling your intuition with how we analyze physical pictures in this class. So imagine a merry-go-round. It's a playground object. It's a kind of circular thing fixed in the center. It spins. People can like stand on top of it. There are rails that you can hold on to. It's a kind of children's thing. Let me draw a representation of that so we have something to look at as we talk about it. So we have a top view of merry-go-round. Imagine it's spinning about the center here. And I guess you are considering someone who's standing someplace on the merry-go-round, maybe near the edge. And this is a top view, so this is their head, this is their body. Okay. And it says, a girl says she needs to hold the safety rail real tight or else she will fly outward. Okay, and I think that's the kind of the feeling that all of us relate to. If you've been on merry-go-round or if you've been spun around before, you get the sensation, well, I have to do something to stay in. Like if I stop doing it, I will, fly outward. So that's the picture we have in mind. Let's just say, so this girl is kind of spinning on the edge of the merry-go-round, and at some point she will reach this point. So if she does suddenly let go, will she indeed fly off the merry-go-round directly away from its center? Oh wait, this is kind of bad position to put her in, so let me actually put her over here. So what you have to think about is her tangential velocity. So she's been moving in circles. So at this point, she's undergoing tangential velocity, moving that way. And as she's moving around, the tangential velocity changes. It kind of goes tangent to the edge of the circle. So at this point, her velocity is going straight to the right. So to the point that it's asking, if she does suddenly let go, will she indeed fly off the merry-go-round directly away from its center? Okay. So this is what it would look like if she was moving directly away from its center. So imagining taking this picture, and if she were being pulled away if she flies off directly away from the center, then at some moment in time she'll be here, and she'll be flying off in this direction. So maybe at the beginning maybe she starts off slower, but then later she's moving faster. So that would be the speed. Or if you imagine tracking our position over time, what we would be saying, if we do say yes, she will indeed fly off the merry-go-round directly away from the center, then we can track her position over time. She would be here, and then later at some time here, and later some time here. And I think as you draw these pictures, you should get a sense that no, that's not what actually happens. And this comes from Newton's first law or Newton's second law, either of those two. Because she has this tangential velocity here, when she lets go, and there's no more force holding her in place, then she's gonna move in straight line. That's how she should move. So at some later point in time, she'll be here, and then here, and then here, and then here, and so on. And I hope as you look at this drawing, you see two interesting things. One is that she does, in some sense, fly off the merry-go-round. The edge of the merry-go-round is right here. So she does fly off in the sense that when she's over here, she's not on the merry-go-round anymore. And you can even quantify, you can look at the distance from the merry-go-round center to where she was. She was at radius away. And at some later time, she is indeed farther away. This distance is greater than the radius. So in some sense, she does fly off the merry-go-round. But what she doesn't do is she doesn't fly off the merry-go-round in this way. So what's pushing her off the merry-go-round is the fact that she was already moving with some speed. So when there stops being a force, then she continues to move in that direction that she was moving. So, ends up that way. Use a diagram to explain your answer. Yeah, that's my explanation. This doesn't happen. And I think once you start drawing the diagram, you can kind of see, yeah, this doesn't actually happen. This happens, and it does kind of match up with how someone flies off the merry-go-round when they stop holding on to it. Yeah, and that's getting at part B. The girl looking directly at the rail she was holding on to, looking at the rail that was here maybe. And she does see that she's getting farther away from that because, yeah, you are moving. And there's actually a bit of a nuance that I want to get to, which is I want to sketch out how the rail moves and how the girl moves. There's actually a complication there that's interesting to look at. Let me get to that after finishing answering C and D. So in C, the girl says, when I let go, I can feel a force pulling me away from the center. And I think this is a kind of thing to make sure that you pause, think about it, and address it. Because this is what she's saying. So, if you think there's a force, you can draw a free body diagram. So let's imagine drawing a free body diagram of the girl in this position. And let's draw it from the top view. So by drawing it from top view, what I mean is we are going to not draw gravity and normal force, because gravity will be into the page and the normal force will be out of the page. And it's just confusing more than anything. Those just balance each other out, so I won't draw gravity and normal force. So this is the question. What this statement says is when I let go, I can feel a force pulling me away. Then she's saying that there's some kind of force pulling her away. And while she's holding onto the rails, there's an inward force. And before, she wasn't flying out because these two forces were balanced. And what she would be saying is, well, when I let go of the rail, then this is gone. And because of this remaining outward force, that's why I fly out. Now, if this explanation sounded convincing to you, then this is what I want you to consider. What force is there that's actually pushing the girl outward? Imagine this picture. So it's, I think, quite easy to imagine what this rail force is. That's the contact force between her hand and the rail touching. That's where the rail force comes from. That's holding her in. So if you're taking this situation seriously and trying to think about where does this outward force come from, if you need to, pause. And the answer of where does that come from is it doesn't come from anywhere. And if you are tempted to answer centrifugal force, so this is what we call a fictitious force or a pseudo force. I think a pseudo force sometimes sounds a little bit better because it sounds smarter. I don't know. Pseudo force that happens in an accelerating frame. And I will give a slightly longer explanation in a bit. But the rule we go by with in this class is we don't analyze the physical situations in an accelerating frame. For those of you who go on to become physics majors, or I think mechanical engineers analyzing some complex situation, you might be in a situation where you will use an accelerating frame, like a rotating frame. For this introductory physics class, what I implore you to stay away from or implore you to do is use inertial reference frame and stay away from using accelerating frames. Because even when you learn to do it perfectly in our context, there will be some complications that you forget about, and it'll lead to mistakes and errors. So what we've drawn here is something that someone might reasonably consider in what we call rotating frame. And by rotating frame, we really mean frame viewed as a perspective of the girl. And I think that's why we identify with it so easily, because that's the reference frame we were in as we are holding onto the rail. And let me address 2 points simultaneously. So, how is rotating frame an accelerating frame? And if you are saying that this is some kind of a strange frame that we shouldn't use, then what happens in an inertial reference frame? So what happens in an inertial reference frame is that this outward force simply isn't there. I mean, it just comes straight from, well, imagine the girl holding onto the railing. What's pushing her outside? Like, no object is touching her to push her outside. And the only non-contact force there can be is gravity, and gravity is pulling her down, not pushing her, outside. So this is the picture, point 1. Now, as you look at it, you can clearly see that acceleration is not 0. If anything, you have an inward acceleration that goes with your net force coming from force of the rail. How, you might ask, but she's staying in place on the merry-go-round. She's not moving inward. How is she accelerating inward? That's where you have to remember that whenever something is moving in a circle, like this girl on the merry-go-round, there is going to be centripetal, center-seeking acceleration. Because your velocity is changing direction from here to here, even when the speed remains the same, there's a change of velocity that's kind of pointed towards the center of the circle. So whenever you have something moving in a circle, uniform circular motion, think centripetal acceleration. There will always be some acceleration. And that's what this acceleration is. And this force with the rail that's providing that centripetal force that can produce the centripetal acceleration. So to the point of why she feels being pulled away from the center, I think the way I would try to explain it is the same way we feel our own weight, the apparent weight. The way we feel our weight, we actually don't feel gravity directly. Like if you're in free fall, you'd feel like you are in microgravity. That's like astronauts in International Space Station. But gravitational force on them is actually pretty significant. It's like 80-90% of the gravity on us. The way we feel gravity is we are not actually feeling the weight that's pulling us down, what we are feeling is coming from the normal force. There are contact force that's pushing us up in a lot of circumstances that's equal to the weight. And that contact force is pushing our feet up. And if we are standing up, then our muscles are contracting in a way that we can stand straight up. And all of that effort that you exert with the normal force, that's what leads to your sensation of weight. You feel like something is pulling you down because in order for you to stay in the same place, you had to push yourself up. And it's the same situation here. When you have this force that's basically trying to keep her at the same radius, then that because you had to exert that inward force, you associate it with the sensation that something else is pulling you away from that effort that you have to exert. The way, because of with the normal force and everything, you have to have a force on you that's upward in order to stay in place. That upward contact force gets interpreted through your experience as something pulling you downward. So that's this kind of long explanation around this setup. And let me come back to one last thing that I was getting at, that there are complications involved in a rotating reference frame that you should be aware of before you are further tempted to use a rotating frame and centrifugal acceleration as a way to analyze a situation that maybe looks complicated if you analyze the inertial reference frame. And I think I can illustrate that idea with this question and the diagram designed to answer. So in part B, we saw this statement or question. The girl, looking directly at the rail she was holding onto, sees herself flying outward from center. Okay, does she see that? Let's take a look. So we have this merry-go-round. I'm just gonna redraw it here because I need some distance and the size to sketch out things. Here's the center. Here are the two railings. Let's say they are moving at some speed. Enough speed that I'm gonna try to space this out in equal intervals. So in equal intervals, she'll move from here to here to here to here to here, maybe to here. Okay, those are kind of equal spacing. So she's moving at a constant velocity, and let's make sure the railings are moving at the same speed. So these, let me just draw one of the railings as a way to kind of track. So the left railing goes from here to here to here. How many did I draw? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think these are about the same spacing as the way I drew her. So let's look at critically what the girl sees as she looks back at this center of the merry-go-round. So you start out with the railing being to her left and watch this line of sight from the girl on the merry-go-round back to the center of merry-go-round. So in this inertial reference frame where, I'm just plotting things as they move, the girl is moving with no acceleration, just moving in a straight line. The railing is undergoing centripetal acceleration, moving in a circle. I think in this picture, everything's clear, nothing so confusing. I don't think I forgot anything. She is moving farther away. All right. Okay, what's there? Let me try drawing this picture in the rotating reference frame. And I think if people were given the task to do, this is how I imagine a lot of people drawing. So let's say I might have to draw this a little smaller. So let's say you got these two railings, and in a rotating reference frame, then these railings would stay in place. That's the rotating reference frame. And you have this girl, and you are thinking, the centrifugal force in the pseudo force in the rotating frame, it points directly outward. So the girl is going to, get pushed directly outward. So let me just draw 1, 2, 3, 4 of these. 1, 2, 3, 4. And you might, someone could naively say, this way of analyzing is equivalent to this way of analyzing. So let's use whatever is easiest for the problem at hand. That's the temptation. Now, watch the picture carefully. See if they are actually indeed identical or comparable to each other. And as you draw these lines of sight, I hope you see that those two pictures are not actually like each other. There are relative positions that are kind of messed up. So I drew these, so let me label this 1, 2, 3, 4, 5. With each snapshot, I drew these railings 1, 2, 3, 4, 5. And you can begin to see that it's not always going to be the case that these railings stay to the left of the girl. Like here it looks like it did, and starting with here, no, the railings begin to like move ahead of the girl. The railings 3 moved far ahead of the girl. 4 moved far ahead of the girl. So in order to get a physical picture in this rotating frame that's actually physically comparable to this is what you have to do. So first two might be okay, but starting with the third one, you really have to start bending the path so that the girl isn't actually on a straight outward trajectory in this rotating frame. Instead, she's in some kind of curvy path. Then you can see that with that path, then now when you draw this line of sight, the railing is to our right as it appears to be here. So the motion of the girl in this rotating frame, it's not simple like a straight line. It's actually this curved path. And if you're interested in how this happens, how to take this into account, what you have to look up is something called Coriolis force. There's another fictitious force that's not centrifugal force, another fictitious force that appears in a rotating frame. And for it to appear, you need some radial velocity, I think. So when you have some radial velocity in a rotating frame, you basically have an effective force that's pushing the thing to the side. That's what that Coriolis force is. And what I had to tell you is, in this class, I haven't given you the tools to analyze a rotating reference frame while including the Coriolis effect, the Coriolis force. And in upper division classes, like the classical mechanics or analytical mechanics, where they do use things like rotating reference frame, they will give you tools how to handle things like a Coriolis force. But for this introductory class, my strongest recommendation to you is to stay in the inertial reference frame, so that you don't have to worry about these sneaky forces like a Coriolis force that you might not have known about. The fact that this railing moves ahead of the girl in its own circle compared to the straight line trajectory of the girl, you didn't have to know that ahead of time. That just comes straight from your analysis, from your picture. But rotating frames involve a lot of complication. So even though it might feel like using centrifugal forces is easier in one problem, it's going to lead you into a path where you're going to see contradiction unless you learn how to correctly handle the Coriolis force. So yeah, that's the explanation I wanted to give. For part D, why does someone sitting on the center of the merry-go-round not feel thrown outward? It's because, the formula for centripetal acceleration is v squared over r. And actually, this version can be a little bit deceptive because you'll say at the center, r is equal to 0. So, why doesn't this blow up instead? So let me write the other version, which is relating it to the same radius and what's called the angular velocity. This is amount of radians per second. And here it would be angular velocity omega squared. It comes down to, there's a relationship between speed v and the display, the angular velocity omega, which is v is r times omega. So so if you're in the center, not only is your radius 0, your speed is also 0. And rewriting it in this form makes it more obvious to you that since omega will be the same for any point on the merry-go-round, your angular velocity is the same for every point on the rigid body. As your r goes to 0, your acceleration will go to 0 as well. So that's so someone sitting in the center, there's no centripetal force needed, meaning they didn't have to hold on to anything to stay in the same place. That's why they don't feel thrown outward, they don't feel moved around, because they're not having to hold on to anything to maintain their place.
So everyone here remembers this conical pendulum setup that I've been using so far for circular motion? Yes? Seems familiar enough? Okay, so let me describe the setup now. So this would be worksheet 5, problem 7. So imagine that I have some string that's attached. So, in the actual demo, it's my hand. But imagine that's a ceiling. And it's attached to a ball, which is undergoing a circular motion. So, yeah, it's undergoing circular motion. Let me actually measure the lengths this time and see how long it is. So the length of the string that we are using, it's about 50 centimeters, right? So I'm going to be actually plugging in numbers this time. So I'll say the length of the string is about 50 centimeters or 0.5 meters. And let's say we are, let me see what feels natural to me. So this is normally what feels natural to me. How big of an angle do you think this is making with the vertical? Like 30 degrees, roughly? Maybe, yeah. Okay, these are rough numbers. So it's making a circular path so that the string makes the angle of theta, which will later plug in 30 degrees, as it makes this circular path. So here's the question that the question asks. What is the period of the pendulum? As in, everyone here knows the term period? Yes? Okay. Yeah, actually, we are going to spend a little bit more time with the circular motion or rotation terminology later. But let me write down a few so that I'm not losing people as I'm using these terms. So let me call this rotation terms. We are going to come back to this when we do rigid body rotation. So I want to just mention this for now so that I'm not losing people now. So when we talk about rotation, there's a cycle, period, frequency, and let me end with the one last term, which is goes by two different terms. Sometimes they are synonymous, sometimes not. Angular frequency, or sometimes angular velocity. So I think these are most common terms that everyone should know when we are talking about circular motion or rotation. Everyone knows what a cycle is? Well, we can measure the angle in a cycle, but I mean as a cycle, as a thing. Like, if I said, one time around the circle, right? Yeah, that's it. Okay, so I'm not going to define cycle because it seems like everyone knows what a cycle is. But you do have to know that for the rest of the description. So the period, the way you would define it is, I'm not going to give you formulas. I'm going to give you descriptions. Period is the time for one cycle. Right? And you can come up with the formulas which would be formula for period. What do you think a frequency is? So how often? Yeah, so with the frequency, what we are going to be measuring is number of cycles. So number of cycles, let's make it easy for ourselves, say divide by 1 second. So it's the number of cycles per some amount of time. Good? And if you want to know the units, frequency is measured in hertz. But we'll come back to that later. Now, angular frequency, I think it's easier to define this in terms of angular frequency. So when you look at frequency, the unit of frequency is a number of cycles per time, right? So frequency is measured in terms of cycles. It turns out for mathematical reasons, often if you're using frequency or period in your formulas, very often you will end up writing down 2 pi. Like that might be the formula that Ranjit was remembering. That 2 pi comes in often for some reason. And in order to reduce the number of 2 pi's you're writing down, one of the things you can do is express those formulas in terms of something called angular frequency, usually denoted with the letter omega. I'll talk about that later. So with the angular frequency, what you're doing is you're measuring the same thing as frequency, except that you're converting from quote-unquote units of cycles to units of radian. The reason I'm doing this scare quotes is neither of them are actually units. Cycle is not a unit, radian is not a unit. They're both just numbers. But we are saying instead of counting cycles, we are going to count radians. So with angular frequency, it would be number of radians per second. And let me write out radians better. Radians per second. And you know what? I'll come up with a formula for this later. As I said, we're going to come back to this later in the semester to use it more fully. For now, I just want you to introduce the terms so that I'm not losing people if I'm using any of those words. Okay, so 1 period. Now everyone knows what a period is. That's the amount of time it would take for this ball to go around and come back. That would be 1 period. And the question is, what is the period of this thing? Okay. All right. Where do we start? So we're not given much. We are essentially given geometric parameters. Length of the string, angle that it's making as it's going in a circle, and we are asked for period. Any ideas where we would start? So Ranjit says gravity, because you feel like gravity is playing a role here, right? All right, so if you're thinking about gravity, what type of problem are we looking at? Force. We are looking at a force problem. That's where I want to start. That whatever, so here the connection from beginning to the end is not immediately obvious to most people. But the very first place that you can start out with is that whatever you are doing, it'll involve forces. It'll involve analyzing forces. Once you realize that, where do you start? You start out with a standard strategy, which starts out with a free body diagram. So I'm going to start out with a free body diagram. I don't know exactly where I'm going with it, but I'll just start there and hope that once I have enough things written down, it'll become clearer. So I'm drawing free body diagram of the ball. And here's one thing you always have to do with the circular motion. Because the things are always moving around, you have to pick a snapshot. You have to pick a moment in time to draw the forces for. So I'm just going to pick this snapshot. For no other good reason than I like this side better than this side. But you could do it for this side. In the end, it shouldn't matter. I'm going to use this snapshot to help me analyze the forces. So Ranjit said this earlier. So there's going to be gravity. Any other forces? Did I hear friction? Tension, okay. Yeah, tension, that's going along the direction of the string. Tension, okay. Any other forces? No, oh yeah, I guess we looked at this before. So does this look like a complete free body diagram? Yeah, this is a free body diagram that's indicating acceleration to the left, maybe. Do you expect leftward acceleration? From what? Yeah, towards the center. Yeah, Stephen, is that what we're gonna say? Yeah, so you do expect acceleration towards the center. So if I'm drawing a snapshot for this point here, I do expect a leftward acceleration. So, all right, so all of this seems good. So, all right, what's the next step? We have free body diagram, that's step number 1. Step number 2. Define coordinate axis. So, all right, I'm gonna do it along the direction of acceleration. So let me define it this way. Positive x is going to left, y pointing up. All right, then I need to break forces down into components along these axes. So gravity is fine, I don't need to do anything. The tension needs to be broken into x and y component. Once I draw the y component, I see the angle that I have drawn before, so let me just draw it there. I don't need to go through complicated geometry exercise. So the y component will be t cosine theta, x component will be t sine theta. Okay, so now I'm ready to write down Newton's second law equations. That's my step number 4. So I write down 2 equations, one for the x direction, one for the y. So net force in the x direction and the y direction. In the x direction, there's only one force, t sine theta. So in the positive direction, the way I defined it, t sine theta is equal to mass times acceleration. Y direction, t cosine theta is minus mg. T cosine theta minus mg is equal to, what is it equal to? Wait. So it would have been normally equal to mass times acceleration in the y and x direction. But what's the acceleration in the y direction? 0 by design. So I'm used to just writing it down as 0 instead of going through all those complicated symbols. Good. So as I keep pointing this out every single time I do this, this is the end of standard strategy. And here, you will see that I don't seem any closer to the answer that I'm looking for. So the answer that I'm looking for is the period. Is period any part of my expressions here? No, so nothing here directly relates to period. So I need to go one step further. Any idea what that one step further is, Stephen?
Pendular acceleration.
Centripetal acceleration. Yeah, you have a formula for that, right? Yeah, so this is the other thing to remember in circular motion. Not only you expect there to be acceleration, you actually know what that's going to be. You know that acceleration will be v squared over r, where r is the radius of the circle. So might as well reflect that in your equations. That'll help you see where you go from the equations you have to the answer you want. So say this is equal to mv squared over r. And I will have to rewrite r in terms of given quantities later, given geometric quantities later. All right. So any idea how we might be able to use these to relate to the period?
Yes.
Okay, Abdi, how?
We have a radius over there.
Okay.
And through radius, we have a circle motion.
So let's say I have radius, and I have some sort of velocity. How can you use those to figure out the period?
So once we know the radius, we can know the circle.
Okay, I know the circumference. And the circumference, or the distance, is equal to 2 pi r. And that will be important in knowing the period.
Then we can find the time from the velocity.
Yeah, so I know the distance, I know the velocity. So this is time. The time taken is, let's see, distance divided by speed, right? Yeah, so remembering this, then period must be, this must be equal to distance, 2 pi r, divided by speed, v. Yep. So let's put it this way. I feel like my goal here should be to find the velocity v. Because once I find the velocity v, then I can calculate period easily enough. So okay, so that's my goal. So you know, here the standard strategy doesn't take you as far as it did in past problems. Here there are these additional dots that you need to connect on your own before you can proceed. So, but once you've done all that, then all right. Then my goal is to find the speed here that's consistent with everything that's written down here. Then I'm back to my regular problem solving mode. I have 2 equations. So the question is, do I have only two unknowns? V is one of the unknowns. Any other unknowns? T is an unknown, okay. Is theta known?
Yeah.
Given, right? Now, R, it's technically not given straight, but you can figure out R. Let me actually do that now. So, in this triangle here, I'm given L and theta, right? So I can express this R as L sine theta. Good? And once I do that, then R is known. So I might as well just to replace this R with L sine theta now so I don't confuse myself later. Good. Okay, so so T is once again, yeah, no other unknowns. So I have two equations, two unknowns. I should be able to solve for it. Yeah. So I would solve the second equation for T, plug it into the first equation to get rid of it. Then I can solve for V exclusively. Okay, let's do that. It shouldn't take that long. So solve the second equation for T. T is equal to mg over cosine theta. I'm not making that mistake again. Plug this into equation 1, then you get mg sine theta over cosine theta. I feel like I've done this before, but let me go. Sine theta over cosine theta, tangent theta is equal to mass times that mv squared over L sine theta. All right, masses cancel. Let me get rid of it. Then I can solve for V here. Move L sine theta over. I get V is equal to square root of GL tangent theta sine theta. Good. Now I'm not actually done. Once I have V, then what I need to calculate period. So let me do that. Period, according to the formula I've written down before, is equal to 2 pi r, or L sine theta, 2 pi times L sine theta divided by all of that. Square root of GL tangent theta sine theta. Let me simplify this a little bit before we start plugging in numbers. I'm going to look at the sine theta as a square root of sine squared theta so that I can cancel out one factor of sine theta from here. I think I can actually cancel out more. This tangent theta here, what it is sine theta over cosine theta. So I can cancel this sine theta with the remaining sine theta. I'm going to look at this L as also, writing it out. It's equal to L squared square rooted. So I can cancel out one factor of L from here. All right, that seems enough. Let me write down a cleaned up version of this. So it's 2 pi times square root of L over G, square root of L over G, times, it's 1 over and then 1 over, so times the square root of cosine theta. Good? Everyone okay with this as the final expression for period?
Can you just go over one more time?
So are you okay with all the cancellations here?
You square and square root sine, and then that's how you cancel.
Yeah, L and sine theta I expressed as square rooted L squared times sine squared theta. Yeah, once you're okay with all the cancellations here, then this is that's just a cleaned up version. Good. So I want to actually calculate the numbers. So this time, so what I'm going to do is I'm going to, try to make this go in a circle the way we were describing, about 30-degree angle. And I'll have you guys measure the period and see if it matches with our prediction. So let me finish this prediction here. I'm just going to plug in rough numbers because it's not going to be better than 20% or so. 2 pi within 20% is 6, right? 2 times pi is 3. So 6 times square root of L was 0.5. So 0.5 meters divided by G within 20%, 10 meters per second squared. And hopefully you are seeing that the units work out because the meters cancel, second goes to numerator, and you're square rooting it, so all the units work out. And cosine of theta, I happened to look up what cosine of 30 degree was before. It was 0.85 or something, right? And when you square root, it's going to be like 0.9 something. So I'm going to say this square root of cosine of 30 degrees is approximately 1 within my precision. Okay? So let me finish this number. 0.5 divided by 10. I don't know what that is. 0.05. Let me write it this way. 6 times square root of, so that's a 5 times 10 to minus 2 seconds. Oh, I think I can do this. 10 to minus 2, that's about 10. So when I do the square root, this will be about 2 times 10 to minus 1 within 20%. Because 2 squared is 4, which is close enough to 5. Everyone good? Yeah. All right, so 2 times 6, so it should be about 1.2 seconds. That's my prediction for what the period should be. Let's see if it is. So what I'm going to ask you to do is, because you guys can see the clock, either that or this better, I'm going to do this, and we'll try to count it for 10 cycles, and then divide it by 10. Good? So I'll tell you to start, and then when it stops, someone tell me how many seconds it was. So let me get it started. Ready, set, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many seconds? 14 seconds? 13 seconds, so 13.5 seconds. So the actual experimental value was 13.5, or divided by 10, 1.35 seconds. It's within 20%. That was my goal, and it's within 20%. Good, that's how it works. This classic problem that you should know how to do. There are homework questions that's similar to this that involves airplane actually. But so this is one of those questions where you can get tricked into making wrong choices easily. So I really wanted to make sure that we go over this problem 8 together. So read the problem while I get the board ready and erase some stuff. I guess I have to do it here. I don't think we will have time for problem 9, but maybe I'll make a video. All the friction does is it just complicates the problem so that it takes longer to do it. It doesn't introduce any conceptual issues. So everyone okay with what the question is describing? Kinda. It's describing, I think I have, I have these toys that you will see eventually soon. So, if we have a road, sorry, I can bend it this way, but if the road is just bent this way, you can see that as the car goes, if the road is frictionless, it won't be able to make turn. It'll just slide off the road, right? Yes? So to help the car turn, in addition, so it's saying that in addition to making this turn, it'll make it banked. It'll make it slightly angled so that, it'll help the car make the turn. Okay. So here so I can draw, I can draw 2 pictures. The top view. So if you are looking at the motion of this car from the top, the road should undergo some circular path, or the road curves along a circle of some radius r. Right? I'm drawing only part of the circle, but the idea is that this would be extending into a full circle if they made the road that way. So this is the top view, and we have the bottom view. Not bottom view. Side view, front view. Let me call it back view. So from the top, let's say this is the car that's going on that road, moving at some velocity v. And imagine looking at this car from behind. If you are looking at it from behind, the back view, then what you should see is that, one, the road will be banked, curved, angled. So this is the cross section of the road, banked at some angle theta. And this is the view of the car from behind with the tires and whatnot. And I think I explained this notation earlier. If we are describing the velocity of the car, we would describe it with this symbol here. This is the velocity of the car. Everyone remember this symbol? It means vector pointing. Wait, I didn't introduce it in this. Yeah, it means vector pointing into the board. So that's the velocity of the car in this back view. Yeah. So you kind of have to describe both of these pictures to describe the motion fully. Because in the back view, it's hard to label this radius r or the velocity. But from the top view, you can't really see the angle of the road. Okay? So this is the description of the setup. And what the question is asking is, what they're eventually asking is the banking angle. So you are specifying the radius of curvature and the velocity of the car. And what the question is asking is, what should be the angle that the road is banked at so that the car doesn't slide down or up. Okay? All right, so let's go through the steps that they're telling us to do. So I hope all of you realize that this is essentially a force problem. You have to analyze forces here to answer this question. So then standard strategy, the first thing you would be doing is drawing the free body diagram. Okay? So let's follow the steps that they're guiding us through and see what we get. So the free body diagram of this car is, well, so I'm going to use the back view to draw a free body diagram, by the way, because most of my interesting forces are vertical, so it's hard to draw that on the top view. So I'll use the back view to draw my free body diagram. So what are the forces on the car? Gravity pulling it down. Normal force, what direction? Like perpendicular to the road, right?
Yeah.
Okay, any other forces? Do we need any other forces?
We say friction.
Friction, like a traction, the force between the tire and the road, right? Now, in normal cases, yeah, there's that force. There's also air resistance. So my question more is, do we need any other forces? Yeah, if we are saying that the car is moving at constant speed v, then we don't need any forward and backward forces. Yeah, we don't need it for now. Or we can say they just balance. And well, it did say, wait, where does it? Oh, it says surface is approximately frictionless. So, we might have thought of a friction going down the hill or up the hill, but the problem says no friction. So this is it. This is the complete free body diagram, and the way the situation is described, we don't need any other forces. So now my second question, what's the direction of acceleration based on this, or what do you expect the direction of acceleration to be?
Towards the center.
Yeah, towards the center. So if I drew it here, this would be the direction of acceleration. If I drew it here, can you tell me what direction how would I draw it? Down the slope or horizontal? Yeah, so this is where I want you to imagine where the center of this circle is. On this back view, center of the circle essentially would be, you imagine extending this baseline to however far the radius is, and this is where the center of the circle is. All right? If you go down the hill, are you pointing to the center? No. You're not. So in order to point to the center, your acceleration has to be pointed horizontal. This is an important realization with this problem, that the direction of acceleration is horizontal, not down the hill. It's also surprising because you have seen the inclined plane problems before, and before, unless somebody was pushing the road or whatever, the acceleration would have been down the hill. And I'm pointing this out that in this case, when you consider everything, acceleration is not down the hill. It's purely horizontal. So, all right. So, all right. And these forces are consistent with this direction of acceleration that we expect. So we are going to move on to next step. What's the next step? Define the axis. I'm going to define it this way, x and y, along the acceleration, right? So once you realize this, then the rest of the steps fall in. Once you realize the acceleration horizontal, then you realize the axis I'm picking is also straight axis instead of tilted axis. Okay, and I need to break down forces into components. That would be n into x and y component. I might have to do a little bit of geometry to figure out this angle theta. So let me draw some auxiliary figures. This is theta that was given to me. So that theta is this theta. This angle is 90 degrees minus theta. So this is theta. Okay, once you know the angle theta, then I can write down the components. This is n sine theta. This is n cosine theta. Okay. All right, now I'm ready to write Newton's second law equations. All of this might actually start to look familiar. Like it's beginning to look like similar to what we did here. But I would go through this step every single time. Because depending on the problem, there could be some key difference somewhere. So I wouldn't just assume they are the same. I would go through step by step to make sure they are. So net force in the x direction and the net force in the y direction. There is only one force in the x direction. That's the x component of normal force. That actually answers part B question. What provides the net radial or centripetal force? What provides that? Normal force. It's the component of normal force that's providing the force that's going to end up being our centripetal force. Yeah. So that's equal. So net force is equal to n sine theta. That's equal to mass times acceleration. And I learned my lesson from last time. Let me just write down that this is centripetal acceleration. So I actually know what it is. It should be mv squared over r. Like I know all of this already. No sense in pretending that I don't know it. Yeah. Net force in the y direction is normal force and the gravity. So n cosine theta minus mg is equal to 0. So this is our end of our standard strategy, plus a little bit of information that I'm plugging in from my other knowledge of other formulas and situations. So let me do a quick check to see if I have the correct number of equations and unknowns. I have 2 equations, so I better have only 2 unknowns. Do I know the normal force? No. Do I know the angle? Here, no, because they are looking for it. I don't need to look at this. Do I know velocity? It's given, yeah. We treat it as given. Yeah, so if the velocity weren't given, I couldn't answer this question. Do I know the radius? Yeah, we also treat it as given. And you can imagine a situation, if you're designing a freeway, you know what velocity cars should be driving at, the speed limit or somewhere close to it, and you know the radius that you're designing for. So these are parameters that you would know as you are trying to design it. All right, so okay, that's it. 2 unknowns, 2 equations, I can solve it. So let me get rid of n by solving for n in the second equation, plug it in, and I'll try to solve for theta somehow. Yeah. By the way, in this set of equations, what you are seeing is that you are seeing both sine theta and cosine theta. And I will tell you the mathematical strategy that I use. The strategy that I'm going for is I want to combine these into one trigonometric function, if that's possible at all. Sometimes it won't be. In that case, you have to write down, cosine theta as a square root of 1 minus sine theta and work it out that way. So, you have to be ready to do that. But usually when you do that, you are going to end up having to use quadratic formula. I don't like using quadratic formula. So my first strategy is to try to combine them into one trigonometric function. Hopefully that'll happen naturally. If it doesn't, we'll see it then. Okay, so solve the second equation for normal force. Then I get N is equal to mg divided by cosine theta. I have done this before. Okay, but even if you have done it before, I recommend that you go through every single step for every single problem. Plug this in here. Yeah, then it's gonna be mg sine theta over cosine theta. So that's tangent theta. So that's the single trigonometric function I was hoping I would get, and I did. So I get mg sine theta over cosine theta, or tangent theta, is equal to mv squared over r. And the masses cancel. Good, because mass of the car wasn't given. If you're designing a freeway, it could be for a semi-truck, it could be for a, well, probably not bicycle, motorcycle. So here I'm going to solve for tangent theta. So tangent theta is equal to v squared over rg. Verify that on the right-hand side, the unit, it becomes unitless. Meter per second squared, meter squared per second squared, divided by meter times meter per second squared. So units cancel out on the right-hand side, as you'd expect. And that's it. I guess if you leave your answer this way, I wouldn't grade it as incorrect. Because oftentimes, this is the cautious form to leave it in. This is especially true if you have a reason to think theta could become bigger than 90 degrees. If it might be in the second quadrant, third quadrant, or fourth quadrant, then you want to be careful how you use arctangent. Here, is this angle going to be bigger than 90 degrees? No. So I can use arctangent then. I can say theta is equal to arctangent of v squared over rg. But I do mean the cautionary note. For every problem, you have to think to yourself, do I expect theta to be an acute angle? If it might not be, then you have to be careful in how you proceed from there. So that's it. That's the angle. That's the angle that would allow the cars to make this turn without sliding up or down. And now, this is not a very realistic situation because there's no friction. So for the realistic situation, this is what needs to be done. But let me actually try making a video for this, and I'll just post it on the course website instead of spending class time for this.